Hello and welcome to today's session. We're looking at energy stored in a capacitor. We have three objectives today: to understand that when a capacitor is charged, it stores energy, to be able to calculate the amount of energy stored, and to be able to solve problems involving the energy stored in a capacitor. So in the last lesson, we saw that when you charge a capacitor, the potential difference across the plates increases in proportion to the charge. And we could plot a graph of voltage versus charge on the plates. And looking at the graph, we can consider charging the capacitor by a small amount, so delta Q. And then if we're going to put more charge on that capacitor, work must be done. So charging from Q to plus delta Q, we have to do work, and we can find the work done by looking at the graph. So that energy change is going to be equal to the area under the graph. And we want to consider the average change under the graph. So we can find the energy by considering the charge and the voltage. So if we want to consider the total energy from 0 to Q, then we'd have to consider the triangle. So the total energy would be half times the charge multiplied by the voltage for that complete area under the graph. So again, showing that on the graph, the whole area we'd consider if we're going from 0 volts to V, or from 0Q to Q, the total energy, because we have a triangle, it's half base times height, and it's going to be half Q times V. So that gives us the energy stored in a capacitor. This equation is on your formula sheet. The energy equation can be rewritten. So we said it's equal to half QV, the energy stored in the capacitor. But because we know that Q is equal to C times V, where Q is a charge, C is a capacitance, and V is a voltage, we can write the energy equation in two different forms. So half QV, if we substitute in, we can have one expression as the energy is equal to half CV squared. We can also express it as E is equal to half Q squared over C. So depending on what you have in a particular problem will determine which form of the energy stored in a capacitor equation you will use. Okay, and looking at the equation as well, if we double the charge or double the voltage across a capacitor, that will quadruple the energy stored. So looking at the form of E is equal to half CV squared, if the voltage is doubled, we get 4 times the energy stored. The other thing to consider with charging capacitors is the energy that is dissipated as heat. So if you've got a power supply or a battery, it's going to transfer energy QV towards our capacitor, but half of this energy is dissipated as heat or resistance through the circuit, and the rest is stored in the capacitor as half QV. Let's look at a question involving the energy stored in a capacitor. So in this question, there's a 10,000 microfarad capacitor. It's charged to a potential difference of 12 volts. The capacitor is then discharged through a filament lamp. So if you look at the diagram closing the circuit discharges through the filament lamp, and we need to find the average power dissipated by the lamp given that the flash of light lasts for 30 milliseconds, and we need to assume that all the energy stored by the capacitor is then transferred to the filament lamp. So the first thing we need to do, if we want to find the energy, we need to find the energy first because we want to find the power. So the energy is equal, so the energy stored in a capacitor, as we've shown, is equal to half QV. But looking at what we have in the question, a more appropriate form, because we've got the value of the capacitor and we've got the potential difference, would be to use half CV squared. So half CV squared. So then what we will do is find the energy, and then we can find the power by dividing this energy by the time that the lamp flash lasts for. So let's substitute our values in. So E is equal to half 10,000. Micro is times 10 to the minus 6, and we've got a voltage of 12 volts. So 12 squared. Put that into your calculator, we get a value of 0.72 joules. So that's the first part. We've got the energy. Now we need to find the power. So from our power relationships, power is equal to the energy transfer per second, or energy over time. So 0.72 divided by 30 milliseconds, that gives a power of 24 watts. So this was ordered two significant figures. Capacitors can be combined in series and in parallel in circuits. So there's a rule for capacitors in parallel circuits when they're in a parallel combination, and the equivalent capacitance is found by adding them together. This is due to the fact that the potential difference across a parallel circuit is the same, and for series circuits the equivalent is a 1 over rule. So 1 over C equivalent is equal to 1 over C1 plus C 1 over C2. Obviously, we can extend that to more capacitors if we have that in a situation. And if you think about that in terms of rules in series, the potential difference adds up in series, and we have the same charge going around in series. So in the same way as what we've seen with resistors for the combination rules, there's combination rules for capacitors. And what we'll do is we'll try a question where we have to use a combination rule for capacitors. Okay, so we've got a circuit with two capacitors in parallel, and we've got a potential difference of 1.5 volts. We need to answer 4 parts to this question. So total capacitance is the first bit. So what is the total capacitance? So it's in a parallel combination. So for the first part, the equivalent or total capacitance is equal to the sum of them, so C1 plus C2. 500 microfarads plus 100 microfarads gives us 600 microfarads, so that's the first part. Second part, what's the potential difference? So we've got a parallel circuit, so we've got the same potential difference across each capacitor. So the value is 1.5 volts. The third part, calculate the total charge. So we've got the equivalent capacitance, and we know the potential difference. So Q is equal to V times C. V is 1.5, and we've got a value for the capacitance, which is 600 microfarads. So 600 times 10 to the minus 6 gives us a charge of 9 times 10 to the minus 4 coulombs. So 9.0 times 10 to the minus 4 coulombs. Final bit is to calculate the energy stored by the capacitors. So we've got the equivalent capacitance of 600 microfarads, and from earlier on we've said that the energy stored in the capacitors is half QV, so half times the charge which we've got from part 3 times the voltage, which is 1.5. Gives us an energy of 6.8 times 10 to the minus 4, and this is to two significant figures. We can apply the energy stored in a capacitor to energy stored in the thundercloud, because we can consider the thundercloud above as a parallel plate and the earth below as a plate as well. So you've got a parallel plate situation. So there are a pair of charged parallel plates, and we can calculate the energy stored. And we've got a strong electric field between the two. And we can calculate the voltage between the ground and the thundercloud if we know the value of the electric field between the two and the distance between the two. So following on from our work with electric fields, potential difference is equal to the electric field times the distance or the separation between the plates. So if we consider the thundercloud to be one plate, the ground to be another plate, we can calculate the potential difference. E is the field strength and B is the distance. So remember, we can have field strength as the volt per meter and then distances in meters. So we'll have the units of potential difference as volts. So that's what we'll do. Distance between the two, and we can find the voltage if we know the electric field strength. So if we've got an expression for the voltage in terms of the field strength and the distance, we can calculate how much energy is stored if the thunderclouds move up and down in position. So energy is stored, was given by half QV, and the expansion of that would be half QED. So we're treating the cloud and the ground as a pair of parallel plates. So if we move to a new height, D dashed, then the new energy stored will be half QE D dashed. And the field strength is going to remain unchanged because it depends on the charge per unit area. So field strength is unchanged for these situations that we're describing here. The increase in energy will therefore be the difference between moving from one position to the other position. If there's a change in position, we can write the change in height as delta D. So moving from one position to the other, the energy stored is half QE delta D, where the change in distance is moving from D dashed to D. So finding the difference between the two. And if we're increasing in the energy, there's work done. So work done is done by this wind overcoming the attraction between the cloud and the earth. So there's work done in order to increase this energy stored. stored, in the same way that we think of the energy being stored increasing for a capacitor. And air has an electric field strength of about 300 kilovolts per meter. So if you exceed 300 kilovolts per meter, you get dielectric breakdown and the charge can pass through the air. So at fields below that, you have the air acting as a dielectric, so it's not allowing the transfer of charge between it. But if we increase the field strength, if the field strength increases due to a different type of thundercloud situation where you have a higher field, then we'll have charge discharging from the cloud to the ground. Okay, so your task is to complete the 23.2 summary questions and upload them via Turnitin. If you have any problems, you can message me via Teams or send me an email. Take care.